Previously, we used the method of unfolding to evaluate this inner product. Here, this F is a holomorphic modular form. Of weight K and level M. And because it's a holomorphic modular form of weight K and level N, the absolute value squared is times y to the k is weight 0 and level n in trivial character. And so it makes sense to take the Peterson inner product with this Eisenstein series of level n in trivial character. And what we found through the method of unfolding, is that this inner product was equal to gamma function of s plus k minus 1 over 4 pi to the s plus k minus 1 times this Dirichlet series n from 1 to infinity. So here I'm going to assume it's a cusp form, in fact. And the Dirichlet series that we get is this, where these an are the Fourier coefficients in the Q expansion of F. So remember, E of whatever is E to the 2 pi I whatever. Okay. Now, we also saw that the residue at s equals 1 of this Eisenstein series at infinity of zs, and here let me say just chi naught. Chi naught is the trivial character mod n, so this is really E zs chi naught. We saw that this was the one pole in the half plane, real part of S at least 1, and the residue that we got was 3 over pi times 1 over n plus 1, and we saw this for n prime, and in general it is equal to 1 over the volume of gamma naught n quotienting the upper half plane, which is equal to 3 over pi times 1 over n times the product over primes p dividing n of 1 plus 1 over p. And we didn't prove this, but it is true. And we can combine these two facts in a productive way. So the way to combine them is to say, well, let's look at this this inner product. So the inner product y to the k, constant value squared of our modular form times E zs bar. This is equal to our integral gamma naught n quotienting the upper half plane of y to the k f of z squared E z s bar conjugate, and then our usual measure, dx dy over y squared. And the residue of this thing at s equals 1 is going to be, well, the residue of this thing at s equals 1, which is, we can just essentially move the fact that we're asking for residue inside. And the residue of, so this is, and this we know, we just wrote it down, this is going to be equal to integral of what we had before times the volume of gamma naught n quotienting the upper half plane with the usual measure. And then this has no dependence on z, right, on x and y, so we can just move it outside, and what we're left with is the Peterson inner product of the modular form f with itself, so by definition this is equal to the norm of f. And when I write the norm of f, what I mean is value of f and f. Okay. And do people, yeah, people normally write a squared here, right? Okay. On the other hand, if we look at this side, this must also be equal to the residue at s equals 1 of how we evaluate, of the expression we got when we evaluated this inner product using unfolding. Now, when s is 1, well, we're assuming the k is an integer greater than 0. So this doesn't have a pole, and this doesn't have a pole. So what we get is that this is equal to the is equal to gamma of k over 4 pi to the k, and then it's the residue at s equals 1 of this Dirichlet series. And the notation here, is it's sort of, this thing does have a name, and the name that people usually give it is as follows. They write it L and then S, and then they have an F and then an O times F bar. So this is O times in LaTeX. And this is known as a Rankin-Selberg convolution. So we don't know what this is. This is mysterious, but because we have this alternate expression for the residue of the inner product, we can figure out what this is. So to summarize, what we have is that the residue at s equals 1 of the inner product y to the k times the value of f squared with our Eisenstein series is equal to this thing we have here but it's also equal to what we had above. And here we had the norm of f. Maybe I'll write this a little bit more clearly, sorry. So just comparing these two things, this gives us the residue, right? So the residue at s equals 1 of this convolution L function is equal to, and then we can just rearrange, is equal to 4 pi to the k divided by gamma of k volume of gamma naught n quotienting the upper half plane times the norm of f. So you see how by using unfolding we could get the value of some inner product, and then by knowing the residues of the things in that inner product, we could also figure out what the residue of the inner product would be in a different way. And then by comparing the two methods, we can get some non-trivial statement. And this sort of thing is actually a very common technique, a very common approach to solving problems.